Hey guys, welcome to lecture 6 of this RISC-V processor design course. And this is one of the most important lectures of the series because we're going to go through the instruction execute, how we compile a program, how we simulate the program with the instruction set simulator that we built, how do we run both the instruction set simulator and the hardware and then compare them together to make sure that the hardware is executing what is supposed to. And this is why I've created a simulation manager, for lack of a better term, and we're gonna see the process of bug fixing. Although bug fixing it's really an art, so I can't teach you art, but I can show you my approach to bug fixing. So let's get into it. For now, we're just going to have an arithmetic and logic unit inside the instruction execute, which has a 1 clock cycle delay and then goes straight to the register file. And let's go see real quick what the top level of the instruction execute looks like. And you can see we have the interface from the IDE 1. We have some info for debug that we're going to use in the simulation manager and whenever we run the test bench to understand what instructions we're fetching. And here we instantiate the ALU. This is the output interface for the write back stage. And again, this is used only for debug. And we're going to see in the upcoming lectures how we're going to wrap this thing inside a define that then we're going to toggle and untoggle when we synthesize it or when we are debugging. So if we go inside the ALU, this ALU has been taken from an open source core that I've worked in the past because I didn't want to redo the effort. And the only thing that I did was to add the output flops to this module. And what this ALU does, it pretty much implement all the functionalities that are needed for RB32I. So you can see here we are preparing the operand for a subtract, or we are taking the immediate if it's an immediate function, or the RS2 value. Here we are understanding what kind of logical operation we are performing. And that's pretty much everything that we do here. There's an output mux to understand if we want to take the result of the add, the logic result, the shift result. There's really nothing fancy here, but the nice thing about this ALU is that it's silicon proven. There are chips out there with this ALU inside. If we take a look at the top level of our core, we can see that we instantiated the EXU, and this set of signals go inside the IDE1 stage. And if you remember, inside the IDE1 stage, we have the register file. So this is the interface that we are using to write back inside the register file. So this is everything there's to the EXU stage. For now, we're gonna see in the next lectures that we're gonna add the load and store units. We're gonna add the control unit to fiddle with the program counter and all this kind of stuff. Now our processor is ready to start executing the first instructions, and we need some instructions to execute. So let's start understanding how the whole toolchain works to compile RISC-V programs. We're going to use the new RISC-V toolchain. There's also an LLVM toolchain, which is in its early development stage. We'll stick to the new one, at least for the things that we need to do is more than enough. So let's jump over the code base, and you have the instructions to install the GCC, so the new toolchain, inside the lecture notes in the repo. We are in the tiny betas tests Oz folder. And we're gonna start with assembly tests because we want to really focus on exercise specific instructions rather than compiling from C, which is going to generate a lot of instructions right now that we don't know yet if they're going to be executed correctly or not. So let's see. We really have one test which is called basic LUI, and let's see what this test does. We have a few things to specify in the assembly file. One is what is the global entry point for our code. So global underscore start means that our program begins at the underscore start label, which is the default one for RISC-V. Then we're specifying that this is the text section of the assembly file, so where the actual instructions are. And then we are specifying the instructions itself. So this is the start label. This is the instructions that we're going to perform. And the ret is a return pseudo instruction. And we're going to use it as our exit sequence. For now, we're going to see that as our tests gets more complicated, we will need to introduce more complex exit sequence to understand when we are done executing. So to compile this thing, we can use the RISC-V 64 GCC by specifying that our architecture is an RB32IM, and so the application binary interface uses 32-bit pointers. Again, this is something that we're going to see into the upcoming lectures, and we're specifying that the text section should have an entry point of this number. Is completely arbitrary, but this number is going to be used as our reset vector. So this is the initial program counter value of our processor, and we are outputting a test binary file from the basic LUI test. So let's hit enter. Let's see what we have inside the test. So we can use the obj dump that is shipped with the new toolchain for RISC-V, and we can see that the text section is disassembled, and this is what it's inside. So we have LUI. Here you can see that X1 has been translated to RA because it's using the application binary interface. You can specify to the obj dump, I think you can, to use the machine naming of the register. So X1 instead of RA, it's not important as long as we remember the mapping between the two. This is the address of the section. This is our the address of the first instruction within the text section. So you can see why the reset vector is going to be initialized to this thing. This is the encoding of the instruction. And that's pretty much it. So those are the two instructions that we had in the S file. And this is what the object file, the ELF file, the binary file, those are all terms that can be used, sometimes are used interchangeably. This is the content of the binary file that we're going to use to test at least the LUI instruction. Now that we have our first test compiled, it is a good time to simulate it and start dipping our feet in what the instruction set simulator does. And to my surprise, the only hardware-ready open source instruction set simulator got deprecated. So I had to build a custom one. It is not open source because I might sell it in the future, but I released a RB32IM executable for you guys to use, and it's inside the tools folder. So let's take a look at it. And the interface is fairly simple. You have the RISC-V sim, And the thing that takes is an alpha file, so a binary file, and it outputs a log. Okay, let's see what the log looks like. So the output of the instruction set simulator looks like. We have the program counter, and as you can see, it matches the actual reset vector. We have the encodings of the instruction. We have the mnemonic of the instruction, and then we have whatever microarchitectural state gets touched by that instruction. So in this case, we have x1 takes this value. Okay, so this is pretty much what the instruction set simulator does. Putting everything that we saw together, we generate a RISC-V assembly test with whatever assembly instructions that we want to test. And with GCC, we generate an ELF file that then goes on one hand on the instruction set simulator and generates an instruction set simulator log. On the other hand, we take that ELF file and we convert it to an hex file to initialize the instruction memory. We feed it to the RTL and we generate an RTL log. And at the end, we compare the two logs to see if we pass or fail the test. And let's briefly jump into the RTL log generation. This happens in the test bench. So here, if we go to the system verilog test bench, we use this little script here. We use this little piece of code to basically sample at each clock cycle if we are touching the microarchitectural state. And in this case, the only microarchitectural state that we are able to touch is the register file. And then we dump the program counter, the instruction, the write back address, and the value that we write back. So if we want to run a code simulation, so if we want to run RTL and the instruction set simulator together, what we can do is use this command where we specify the name of the test and the simulator, which in this case is called Verilator. So this was extremely fast because I had already everything compiled. If we look at what we generated, there's this work directory. Inside the work directory, you can find all the tests that we run. And here you have a bunch of things. You have the ISS log, you have the RTL log, and you have the simulation log. And you can see we have a result mismatch at program counter, the first instruction for this instruction. The ISS says that this should be the value, while the RTL is emitting this value. So we have an error that we're going to debug in a few seconds. But before doing that, let's take a look at what the simulation manager does. And you can open up Tools, Sim Manager, and here you have the code. And there's a bunch of Python stuff, but basically what is going on here is the first thing that it does for each test is to run the generation of the ELF file. So let's jump to the rungen function, which is up here. And you can see that we are calling RISC-V with this, all the parameters that we need and the correct reset vector, so the correct entry point. Then we run the ISS the same way we run it before manually. Then we prepare the instruction memory. So here, what we do is we take the ELF file, we decode it with a Python library. We take the text section, then we dump the content of the text section inside the instruction memory. And you can find the hex file here. Inside the folder, you can see it's imem.hex. And you can see if we go at the top, you can find the two instructions that we saw previously in the object dump. So that's one thing. The other thing that it does is then run the actual simulation. So I've added support for another simulator here. This is a 4-state simulator. We're gonna see it in a bonus lecture. So here we run the simulation, and there's really nothing interesting here except the fact that we pass a couple defines. So we pass this ICCM init file, and we pass the reset vector. Those things get written on the top level test bench where you have those two defines. So ICCM init file and reset vector. So this gets mapped here by the sim manager, and then we run the Verilog simulation as usual, and at the end we compare the results. And here is what we do. We do a little bit of pre-processing. We create some dictionaries to keep track of everything that's going on in both the ISS and the RTL, and then at the end we compare and we check for errors, which can be a PC mismatch, instruction mismatch, or a result mismatch. So that's pretty much everything that we support right now. This thing is gonna grow like a crazy over the next few lectures because we need to support more tests, more exit sequences, branches, and all this kind of stuff. But for now, it's a very simple but effective simulation manager. Now, since the test is failing, we can debug whatever is happening here, and there's no really right or wrong approach here to debug as long as you fix the bug, but there are fast and slow ways of doing it. So the log already says that we have a mismatch in the actual result. So let's take a look at the waveforms and see what kind of mismatch we have at the output, and then we can trace it back and see where it originates. So we know that write back happens from the EXU, so we can take a look here, and here we have the data that we are writing back, which is wrong. And now we have to understand what kind of instruction we have. So we need to understand what the instruction does, and there's no better way than looking at the spec. So let's search for LUI. So LUI is used to build 32-bit constants and uses the U type format. LUI places the 32-bit U immediate value into the destination register RD, filling the lowest 12 bits with zeros. So let's take a look at the waveforms. And if you remember, the instruction that we executed was, we can take a look at the log, and the instruction that we executed is this LUI x1 0x10. So this is the immediate value, and we are writing the immediate value as it is to the write back, to the register file, without doing the 12-bit shift. So my guess is that what is wrong is in how we generate the immediate. And if you remember, immediate generation is in the IDU stage, right in the IDU 0. And as you can see here, this is what's happening. We are taking the immediate here. One option that we have is to extend this interface with 32-bit and do the shift here, or do it inside the ALU. Since I don't want to touch the ALU, let's do it here. So let's extend the interface. So this should now become 12 we have 32 minus 12 should be 20. This should be 20, 20. We probably made some errors, but Verilator is gonna find out. Here, what we should do is we should take this thing and then pat it down with 12H0. Now what we should do is we should extend this immediate interface. This should become xlen minus 1, and this should become xlen minus 1. Let's see if it works. Let's go here. Let's rerun the test. And now the test passes. So we fixed the bug with a very fast decode session, but that's basically how you find bugs. You get at the output, you trace it back, you see what the reference spec tells you, see if you made some implementation errors, and that's pretty much what you should do. So what's next? Typically here, when you start having something work, is that you want to run regressions test, because on one hand the development needs to continue, meaning that we will implement more functions, more stuff, but you don't want to break what is already working. So typically here it is a good moment when you start building what is called a smoke test list, meaning you start adding some tests that run whenever you push to your repo to make sure that a commit that breaks everything doesn't go through, and gives a chance to the developer to fix the bugs before breaking everything. This is ideally done by setting up a CI/CD pipeline, and I'm gonna have a bonus lecture on this. And that's pretty much it. The CI/CD pipeline implementation really depends on the repository that you're using. So if you're using GitLab, it's gonna look, you're gonna set up a YAML file. If you're using GitHub, it's gonna be called, I think, GitHub Actions, something like that. But anyway, each of the big like repository vendors, they have their own version of a CI/CD pipeline. So that's a wrap on today's lecture. Make sure to tune in for the next one, as we're gonna start developing some performance features here, and we're gonna see some very cool stuff that happens even in such a simple pipeline. So I'll see you on the next lecture.